Okay, hello everyone. I am Siddhartha Pramanik. I am a PhD student from the Department of Mathematics, IIT Kharagpur. So, this is the problem solving session for the week 3 of the course Computational Commutative Algebra. So, as usual, before start solving some problems, I will list down the topics that are taught in this week so that it will help you to summarize the contents. Okay, the keywords of the topic. We have started with the proof of classical Hilbert-Null-Stellenza, and using this, we have saw the radical membership test. Means when an element belongs to radical of an ideal. Okay, so next uh, we have seen that if we take an ideal I and take a generating set for that ideal, then that generating set may not be a Grobner basis. So how to check a generating set is a Grobner basis or not? So that is the Buchberger's theorem. Next, using this, we have given an algorithm to produce a Grobner basis from a generating set, and we have called it Buchberger's algorithm. Then we know for an ideal I, the quotient ring R mod I is also a K vector space where R is the polynomial ring. So we have seen how to find a K vector space basis for this quotient ring R mod I where I is any ideal. Then we have seen some criteria that when the variety of an ideal is finite, okay, when this is finite, and after that we have seen how to eliminate variables, means elimination of variables. And as an application of this, we have seen how to find kernels of ring homomorphisms from polynomial rings to polynomial rings. And then we have introduced the module theory. So we have seen modules, definition and some examples of modules, and basically some basics of module theory. So these are the contents. Now let's start solving some problems related to this content. Okay, so the first problem is basically from the practice problem sheet. Okay, so for this, so we have seen in the lectures that if we take a ring homomorphism phi from R to S, and if we take an ideal I of R, and if we extend it, then we call it I times S. Now again we can contract it back, and then we call it IS intersection R. So this is an ideal of R, and this ideal always contains I. But in our previous live seasons, we have seen some examples that this equality may not hold. So in this problem, we will see a sufficient condition for this ring homomorphism, uh, so that this equality will hold for any ideal I of R. So let phi from R to S be a ring homomorphism. Now, if there exists an R module homomorphism, so phi from R to S is a ring homomorphism. That means S is an R module. So both are R modules. So we can talk about module homomorphisms between this. So if there exists an R module homomorphism, let's say pi from S to R, such that pi compose phi is equals to the identity map on R. Okay, then for every ideal I of R, if you take extension of I to S, and again if you contract it back to R, then it will be equals to R. So this is an arbitrary ring homomorphism. We are saying we have a ring R module homomorphism from this side S to R, such that the composition is identity on R. Then the contraction of extension of any ideal will be equal to the original ideal. Okay, so let's see a proof for this. So one side always holds. Now I is subset of IS intersection R. So this holds always. So we need to prove the other containment. So to prove I contains IS intersection R, let's take an element. Let's say X belongs to IS intersection R. Now by the definition, phi of X must belongs to I times S, and this implies phi of X is equals to summation Si times Yi, where I equals to 1 to n, where these SIs are coming from S and YIs are coming from uh, phi of I. Because the reason is this IS is basically the ideal generated by phi of I. So again we can write this as summation si phi of some xi I equals to 1 to n, where this xi belongs to I. So this is because yi belongs to phi of I. So now, so what we have to prove? We have to prove that we have taken x from this is intersection R. We need to prove x belongs to I itself. And what information is given, that pi compose phi is identity on R. So let's apply pi on this equation. So this will imply pi of phi of x is equals to pi of summation I equals to 1 to n si pi of xi. Now pi compose phi is identity. So this is just x. And this summation will break in pi of si pi phi of xi, where I is equals to 1 to n. Again you apply pi compose phi is equals to identity here. So you will get summation pi of si xi. So this is because pi compose phi is identity on R. Now this belongs to R and this belongs to I. So this summation will belongs to I. So this belongs to I. So that implies, so this implies x belongs to I. So what we have proved, that is intersection R is subset of I. So we have already proved the other, so other side holds always, and now we have proved this, so equality will hold. So is intersection R is basically equals to I. Okay, so let's see the next problem. So this is also from the practice problem sheet. So write down a presentation matrix for the following ideals. So the first one is the ideal generated by 2 when the ring is ring of integers. B is ideal generated by x square when the ring is just kx, polynomial ring in one variable. C is the ideal generated by 2 in the ring Z mod 4z, and D is when I is the ideal generated by x comma y and square of it, and your ring is k x comma y. Okay, so let me recall what does a presentation matrix means. So if you take a ring R, and if you take a R module M, which is finitely presented, so finitely presented means there exists an exact sequence, let's say R power M to R power N to M to 0. So this there exists an exact sequence like this, means M is finitely presented. Now this map is a map of three R modules. So this map can be represented as a matrix. So let's call this map as phi. Then this map has a matrix representation. So that is called the that is an uh, presentation matrix of this module M. So this matrix need not be unique, because if we change basis, then the matrix will also change. So let's see, let's try to find this presentation matrix in these following cases. Okay, so let's see the first one. So here M is this ideal I generated by 2. So for I equals to ideal generated by 2 in the ring R equals to Z, so observe that if you take I here and if you take R here, if you take the multiplication by 2, then this is an isomorphism. So that means I itself is a free module. So here R power M is basically 0. So this means this matrix is 0. So here a presentation matrix for I is just 1 by 1 matrix, and it is whose entries is 0. So let's so one, part A is done. Let's see the part B. So in part B, I is the ideal generated by x square, where R is the polynomial ring Kx. So here also the same thing will happen. So if you see that 0 to R to I to 0 and multiplication by x square is an isomorphism. So here also a presentation matrix for I is the 0 matrix, 1 by 1 0 matrix. Now let's see the part C. So here I is basically ideal generated by 2 bar, where your ring is Z mod 4Z. Yes. So let's try to find a exact sequence like this. So an exact sequence of involving n is called an finite presentation of n. So let's find a finite presentation for I. So I is basically 2 bar. So that is actually ideal generated by 2 in Z mod 4Z, so which is basically 2Z mod 4Z. So let me write 2z mod 4z. Now if we take r here, so it is basically z mod 4z, and if we multiply it by 2, then we have a surjection. So this is exact. Now what is the kernel of this multiplication by 2? This is again 2z by 4z. So this kernel here, it is not 0. So this map will not end here. So again we need to take multiplication by 2. So what we will do, we will get a map here which is multiplication by 2, and we will just use this composition to get a map here. So this is also multiplication by 2. Then you can see that this sequence is exact. This sequence does not end here, but we got a finite presentation. And here the matrix is just multiplication by 2, means map is multiplication by 2. So a presentation matrix is just a singleton matrix whose entry is 2. So a presentation matrix for I is let's say 2 bar. So these three are easy actually. Now let's see the part D, which is little bit complicated. So here the ideal is ideal generated by x comma y and its square, and R is actually the polynomial ring in two variable x comma y. So here I is just x square comma xy comma y square. So we need to find a finite presentation of this ideal I. So let's see how to do this. So let's take I here first. So I has three generators. So we will take r power 3 and a surjection. So what it will map? So here it has standard basis E1. So E1 is basically 1 0 0, and I will map it to just the first generator x square. Let's take the second standard basis vector 0 1 0. I will map it into the second generator xy, and the third standard vector 0 0 1 to y square. So now we need to find the kernel of this map. So let's call it xi for now. So we need to find kernel here, kernel of xi, so that it will be a sum module of this. Now what is kernel of xi? So let a e1 plus b e2. Let's take an arbitrary element from the kernel. Okay, so any element of r power 3 looks like this, where a b c is in r. So that will imply phi of a e1 plus b e2 plus c e3 equals to 0. So we need to find possibilities of a, b and c, right? Now if this is 0, so a is an element of R and phi is an R linear map. So this is phi A will be just A, So this is a times phi e1 plus b times phi e2 plus c times phi e3 equals to 0. Now this implies phi e1 is x square. So let's write this: ax square plus bxy plus cy square equals to 0. Now using this relation, we need to find a, b and c. So how to find this? So there are no particular method I know, but what I usually do is, so now assume if a is 0, then bxy is equals to cy square minus cy square. So this is an equation in R, and R is a UFD. So what can you say about B and C? So that will imply, so we need to take B equals to just Y and C equals to X. Then you can see that this equation will satisfied. And in this case, what will be this element? This element is basically uh, 0, B is Y. Okay, so we need to take B equals to minus Y. So this is minus Y and this is X. Now we will take B equals to 0. Then ax square equals to minus by square. This is also in R. So again use the relation in UFD. That means y square divides RHS. So y square has to divide LHS. That means y divides LHS. So in this case, A must be minus y square, B must be x square. So your vector is minus y square. Okay, it is C. Sorry, my fault. So C equals to x. So B equals to 0 and C equals to x square. And the other case is if C equals to 0, then it is just ax square plus bxy equals to 0. So that will imply a equals to minus y and b equals to just x. So then your element will be minus y, x and 0. So we have got three vectors in R3, but R3 is a tree of rank 3. So it cannot have more than 3 elements which are linearly independent. So we have got at most 3. But one thing you can notice that this element can be written as linear combination of these other two elements, because now minus y square 0 x square, this is y times y is an element of R, minus y x 0 plus x times 0 minus y x. So this element is actually redundant in the kernel. So one can check that kernel of Jai is actually uh, generated by this two vectors minus y x 0, 0 minus y x. So one can check this by using Macaulay tool. It is not very difficult. So one can check this. The kernel is generated by these two elements. Now let's come back to the presentation. So we have taken I, we have taken R3 and map it to I, and we have got kernel which is generated by two elements. Now we just need R2, then we will map it to R3. So here actually we have kernel of Jai. So we are mapping it here, and we are taking inclusion map here, and this phi map is basically the uh, phi is basically composition of I and F. And how F is defined? F of E1 is actually minus y x 0. F of E2 is actually 0 minus y x. So what is the presentation matrix? A presentation matrix for I is, so here it is mapped from R2 to R3. Matrix will be 3 cross 2. Just write these vectors. So minus y x 0, 0 minus y x. Okay, so I hope it is understandable. Okay, so we have done all four parts. Okay, so let's move on to another problems. So problem number 3. So it is about when a ideal of a ring is free R module. So let I be an ideal of a ring R. So then I is a free R module if and only if I is a principal ideal generated by a non-zero divisor. So I is a principal ideal generated by a non-zero divisor. So I will use NZ for non-zero divisor. So it's very simple problem. So let's prove this. So basically I is free R module if and only if it has to be a principal ideal and it is has to be generated by a non-zero divisor. So one part is easy as usual. So which one is easy? So I think this implication is easy. So let's prove this first. So let I is a principal ideal generated by X, where X is a non-zero divisor of R. So we need to prove I is a free R module, right? So if we can prove that it is isomorphic to a free R module, then we are done. So then phi from R to I defined by the multiplication map. Let's say phi of R is equals to just x times R. One can check that this is an R module isomorphism. So that is easy to prove by using this condition that X is a non-zero divisor. So it is very simple. Is an R module isomorphism. So let's check this. So that is for you. So it is isomorphic to R as a R module, and R is free R module. So I is a free R module. So I is a free R module. So one side is very easy. Now let's prove the non-trivial part. So that is also not difficult, but let's prove this. Now the forward implication. So let I be a free R module. So what we have to prove? We have to prove that first thing is I is a principal ideal. That means it is generated by a single element. And second thing, we need to prove that the generator has to be a non-zero divisor of the ring. So let's prove that it is a principal ideal first. So we will use contradiction. So suppose I is not a principal ideal. So every generating set of I must contain at least two elements. So then uh, every so so it is not a principal ideal means it cannot be generated by a single element. Thus every generating set of I must contain so every we can take minimal generating set also. So then every minimal generating set of I must contain at least two elements. So let x and y be two elements in a minimal generating set. Minimal generating set of I. So since they belongs to a minimal generating set, these two elements must be linearly independent over R. So x comma y must be linearly independent over R. But you can see that if you take minus y, which is an element of R, times x plus x, which is an element of R, times y, this is a 0. So these two elements, here is an R linear combination of these two elements which gives 0. So this shows that this element is linearly, this set is linearly dependent, which is contradiction. So this is a contradiction. So that means what we have assumed is wrong. So what is wrong here? So we have to assume that I is not a principal ideal. So that thing is wrong. So hence I is a principal ideal. So we have proved one part, that I is a principal ideal. Now we need to prove that the generator must be a non-zero divisor. So let's take a generator. So let I is equals to generated by X. Now we need to prove that X is a non-zero divisor. So a singleton, so this is a free module, right? Now this is a free R module, and this X is a generator. So this has to be linearly independent because it's a free module. So it must be a basis. So that will, so that implies that X is linearly independent over R. So that implies R times X equals to 0 only when R equals to 0. So that implies X is a non-zero divisor of the ring R. So that is very easy. So this completes the proof that when an ideal of a ring is a free R module. So the proof is very easy, but one just need to uh, recall this. Okay, so let's move on to another problem. Problem number 4. So so if we take an ideal I in a polynomial ring kx1 up to xn, so we know that how to find Grobner basis for I by using the Bookberger's theorem or algorithm. But when I is a principal ideal, in that case, it is very easy to find a Grobner basis. So let's see how. So let I subset of R, where R is the polynomial ring in n variables, be a principal ideal. And also let this is a monomial order in R. Okay, so I is a principal ideal, and we have taken a monomial order in the polynomial ring. Then any set, any finite set, because Grobner basis has to be a finite set. So any finite set G containing a generator of I is a Grobner basis for I. So here the monomial order does not matter actually. So if you take a principal ideal and if you take any finite set which contains a generator, then that finite set has to be a Grobner basis for the ideal. So let's prove this. So let I is okay. So let G be a Okay, that set has to be actually finite set. The Grosvenor basis has to be subset of the ideal. So G subset of I. So let G be a finite subset of I containing a generator, let's say X of I. So generator means, so I is principal. So then I has to be generated by this element X. So what we need to prove that G is a Grosvenor basis for I. So we want to show that G is a Grosvenor basis for this ideal I. So what is the condition? That initial ideal of I has to be generated. So that means initial ideal of I has to be generated by the set initial elements of the set G. So one side is always clear, which is this side. This containment always holds. So this containment always holds. We need to prove the reverse containment. So let uh, U belongs to initial ideal of I. So that means U equals to initial of some polynomial f. So U is non monomial, uh, where, okay, so for some f belongs to I. So U is a monomial in the initial ideal of I. That means U has to be initial term of some polynomial of I. But uh, so f is in I and I is generated by X. So f has to be some G times X for some G belongs to the ring R. Now this implies initial term of f is initial term of G times X and initial term of product of two polynomials, which I have already proved in the previous live sessions, that this is initial term of G times initial term of X. So this implies now initial term of X is in the set, in this set. This implies initial term of f belongs to initial term of some, let's say R, where R belongs to G, and you take the ideal generated by this set, and initial term of f is actually our U. So U belongs to, so we have taken U from initial ideal of I and U belongs to this set. So initial ideal is subset of this. Hence initial ideal of I is equals to initial ideal generated by the elements of initial elements of this set G. So G is a Grosvenor basis for I. So in particular, the generating set X itself is a Grosvenor basis. Okay, so let's do another problem. So this is problem number 5. So let's write it down. So let I subset of R equals to the polynomial ring K x1 up to xn be an ideal, and also let a monomial order, let this greater than be a monomial order on R, and also let's take an element F from R. Then so that so that this element F can be written as some G plus R. So where this G belongs to this ideal I and R belongs to the ring R, such that no term of I is divisible by any element of the initial ideal of I. So this is the first thing. So F can be written as some G plus R, where G is an element of the ideal and R is some element of the ring, and R has some special property that no term of this is no term of R. No term of R is divisible by any element of the initial ideal of I. Now second one is this G and R has to be unique. So if F equals to G prime plus R prime equals to G plus R, where G prime belongs to I and R prime has the property mentioned in part A, then so that G equals to G prime and R equals to R prime. So that means this G and R are unique. So this is an actually easy application of the division algorithm and division by the Grosvenor basis of an ideal. So let's prove this. So first of all, let G be a Grosvenor basis for I with respect to the monomial order, the given monomial order. So if we divide an element by a Grosvenor basis, then we know that the remainder is unique. So that is a property of Grosvenor basis. And also let G equals to some G1 up to Gm. So then by division algorithm, so if we divide F by this Grosvenor basis G, we will get some Q1 G1 plus Qm Gm plus R, where this Qi belongs to R and no term of R is divisible by initial term of this Gi for all I. So no term of R is divisible by any of initial term of Gi. But that initial terms will generate the initial ideal of I. So this implies F equals to some G plus R, where G is equals to summation Qi Gi. This must be belongs to I, because these Gi's are element of G, which is a Grobner basis of I. And no term of R is divisible by any element of initial of Qi. Initial of Gi. I equals to 0 to n. So that will imply no term of R is divisible by any element of initial ideal of I, because this set will generate the initial ideal of I, because Gi is forms a Grobner basis of I. So this proves the first part. So this is actually very easy. Now let's prove the second part. So this is first part. Now second part. So we need to prove the uniqueness of this G and R. So let F equals to G prime plus R prime equals to G plus R be such two expressions of F as mentioned in part A. So we need to prove that G prime is equals to G and R prime is equals to R. Now observe that uh, G prime plus R prime equals to G plus R, and this implies G minus G prime equals to R minus R prime. So what I am doing is basically, so F minus F equals to 0. So that implies G prime plus R prime minus G plus R equals to 0. That implies this equality. So this now this implies R minus R prime belongs to I, because G and G prime belongs to I. So this element belongs to I implies initial term of R minus R prime must belongs to initial ideal of I. So this is a monomial is in this ideal. So this monomial must be divided by, so initial term of Gi must divide initial term of R minus R prime for some I, because G is a Grobner basis, because G equals to G1 up to Gm is a Grobner basis for I. But what is initial term of R minus R prime? So it is either initial term of r if r minus r prime is non-zero. Okay, so let me write. So if r minus r prime is non-zero, then that will imply initial term of gi divides initial term of r, or initial term of gi has to divide initial term of r prime. But none of this case happens because of the property in the first case. No term of r is divisible by any element of initial term of r. So that implies r minus r prime has to be 0. That means r equals to r prime. So if r equals to r prime, then g has to be equals to g prime. So we have proved the uniqueness also. So actually I need to write that. So if this is non-zero, then initial term of gi must divide a non-zero term in r minus r prime, and terms of r minus r prime are just terms of r all and also terms of r prime. So this is a contradiction. So which is not possible by the hypothesis. So r minus r prime has to be 0, hence r equals to r. So this expression is unique. Any element of the ring can be expressed as some element of the ideal plus some element, some plus some remainder, and those elements are unique. Okay, so now let's see an application of this. So this is problem number 6. So let I subset of this polynomial ring kx1 up to xn be an ideal and G be a Grobner basis for I with respect to some monomial order, let's say this greater than. Now let f and g be two polynomials in R. Now the first part says, so we know that if we divide this f by this Grobner basis g, then this remainder of f is unique and we denote it by rem of f subscript g. Now let's see some properties of this remainder. So first thing is uh, f minus g belongs to I if and only if remainder of f when divided by g is same as remainder of g when divided by the Grobner basis g. Second is if we take the sum f plus g, and if we take the remainder of this polynomial when divided by g, then this is same as remainder of f when divided by g plus remainder of g when divided by g. So let's prove this. So first part. So before proving these two parts, let f equals to some q1 plus remainder of f when divided by g, and g equals to some q2 plus remainder of g when divided by g. So that will imply f minus g equals to q1 minus q2 plus remainder of f plus remainder of g. Now note that q1 and q2 is in the ideal I. So now let's see the part A, which says f minus g belongs to I. Okay, now let's see the now if we use the previous problem, that one can express any polynomial as a polynomial of I plus some r, where g and r are unique. And also f minus g can be written as some q plus remainder of f plus g. Sorry, remainder of f minus g, where this q must be in I. So by previous problem, this q has to be q1 uh, minus q2, and remainder of f minus g. Okay, this should be minus, equals to remainder of f minus remainder of g, by the uniqueness. Actually, by previous problem means part B. So let's prove the first part. So f minus g is in I if and only if the remainder of f minus g when divided by g is 0, and that is if and only if remainder of f minus remainder of g is 0, that is if and only if remainder of f equals to remainder of g. Now part B is actually follows the same way. So f plus g is some q prime plus remainder of f plus g, where this q prime belongs to I. So by the uniqueness of q prime and this remainder of f plus g, we get q prime is actually q1 plus q2, and remainder of f plus g is actually remainder of f plus remainder of g, and these remainders when divided by the Grobner base is g. So this proves the second part also. So these are very easy applications of this Grobner basis thing. Okay, now let's see some different problems. About this finiteness. Okay, let's go back to the topics. Okay, now let's see some problem about these varieties. So this is problem number 7. So consider the ideal I, which is generated by x square minus y, comma y plus x square minus 4 in the ring R equals to cxy, which this is the polynomial ring in two variables over the field of complex numbers. Then the first problem is, what is the cardinality of the variety of I? Second one is, what is the dimension of R mod I as K vector space? Third is, find a K vector space basis for R mod I. So in the lectures we have seen that this cardinality of the variety is finite over and where the base field is algebraically closed if and only if this dimension is finite, and if and only if if and only if this dimension is finite, and we have seen the description for a K basis for R mod I, that is the set of all monomials uh, which are not in initial ideal of I. Okay, now let's do this one by one. So here the ideal is x square minus y, comma y plus x square minus 4. So we need to find the variety of I first. Then we can find the cardinality. So to find variety of I means we need to find the set of all common zeros of these two polynomials. Now first let's write this ideal in a simple way. Now observe that, so if I subtract this one from this generator, what we will get? Y plus x square minus 4 minus, okay, let's add, not subtract. Then we will get 2x square minus 4. So this is also in the ideal I. So we can write I as x square minus y, comma y plus x square minus 4 comma 2x square minus 4. So we can write this because this element belongs to this ideal, so this is a redundant generator, but it is fine. But uh, if I subtract this one from this one, we will get this generator. So this generator is irredundant. So we can write this as x square minus y comma 2x square minus 4, because 2x square minus 4 minus x square minus y will basically give you y plus x square minus 4. So we are actually changing the generators. Now again, in a similar approach, we can write I as x square minus y comma 2x square minus 4 and 2y minus 4. So we are taking this generator minus 2 times this generator. Again, we will see that this one is irredundant. So we can write this as 2x square minus 4 comma 2y minus 4. This is because x square minus y can be written as half times 2x square minus 4 minus 2y minus 4. And C is a field, so they are these are generated by x square minus 4 comma y minus 2. So we have find some decent generators. Now let's use this description. So in part A we need to find the variety of I. So variety of I is basically variety of these two polynomials x square minus 4 comma y minus 2, which is basically variety of x square minus 4 intersection variety of y minus 2. So this polynomial vanishes at okay, I have made some mistake. This should be 2. Okay, so variety of this one is just plus minus root 2. So this is plus minus root 2 comma 2. So that means cardinality of variety of I is basically 2. So this gives a solution for the part A. Now part B. So what is the question? So what is the dimension of this armored I? So what is armored I first of all? So this basically looks like some uh, polynomial fxy in two variable plus I, where this fxy belongs to R, which is c x comma y. Now note that our ideal is generated by x square minus 2 and y equals to 2. So in R mod I, y is equals to 2. Sorry, y minus 2 belongs to I. That means y plus I is same as 2 plus I, and x square plus I is also same as 2 plus I. So if we write a general form of this element, only a0 constant term, a1x plus these two term will survive, and all other things like a2y plus a2xy, sorry, these things will be absorbed in I, because y can be replaced by these two, so this a2y will be merged as this constant term. So this thing is basically some a0 plus some a1x plus I, such that a0 and a1 belongs to C. So dimension of this vector space is basically 2. And this also gives a basis. Hence 1 bar comma x bar is a k basis for R mod I. So dimension of R mod I over k is basically 2. So observe one thing, that the cardinality of the variety and the dimension of this quotient is same here. So one natural question is when these two things coincide, when this equality will hold. Okay, so let's address this question. This is problem number 8. So let K be an algebraically closed field and I subset of this polynomial ring in n variables over K be a radical ideal. And also assume that variety of this set is finite. Okay, then prove that cardinality of this variety is same as dimension of this R mod I over K. So basically, when to get the equality of this variety, cardinality of the variety and the dimension of the quotient ring as vector space, it is sufficient to have this ideal a radical ideal. So let's see a proof for this. So since the variety is finite, let V of I is basically A1 up to AR. Now I is radical ideal. Now I equals to radical of I, and this is equals to the ideal of variety of I. This is by Hilbert, Nullstellensam, and Zahn, because our field is algebraically closed. Now this ideal of V of I is basically ideal of these points A1 up to AR. And this is same as intersection of the ideal of the singleton sets. and ideal of a singleton set corresponding to the maximal ideal at that point. This is also one Hilbert-Nash-Stellenza, because maximal ideal corresponds to points and points also corresponds to maximal ideals when the field is algebraically closed. So this is I equals to 1 to R. So now, so what we have got, that ideal I is intersection of finite number of maximal ideals. So where MAI is the maximal ideal how do you write this? Okay, which is I of the singleton set AI. So now, so we have gotten description for this ideal I. Now let's, what our target? We need to prove that dimension of this quotient is the cardinality of the variety. So let's see a description of this quotient. So what is R mod I? So this is same as R mod intersection this MAI. I equals to 1 to R. Now this is isomorphic to R mod MAI cross R mod, sorry, MA1 MA2 cross dot dot R mod MAR. So this is by Chinese remainder theorem. Because these are maximal ideal, so they are pairwise coprime. And all these are vector space, K vector space. So these are isomorphic to K cross K R times. So this is isomorphic to K power R. And remember that R is the cardinality of the variety. So dimension of R mod I over K, which is basically R, and which is the cardinality of V of I. So that is what we wanted to prove. So for this we have used that Hilbert-Nash-Stellenza. So we need the basic fact that the field is algebraically closed. But from this proof you can see that if I is not radical ideal, then we also have this description for the R quotient radical of I. So let's put me as a remark. So in general, so when I is not equals to radical of I, so also includes the case that, so when I is not equals to radical of I, so we know that V of I equals to V of radical of I. These two varieties are same, so their cardinalities are also same. So this implies this cardinality of variety of radical I is same as this vector space dimension. So we got a formula for the cardinality of the variety of I, which is the vector space dimension of R mod radical of I. So the proof is same by the previous. One can just mimic the proof to get this formula. And also one side can be proved that this dimension is basically less equals to dimension of R mod I over K. But this requires a proof which is not trivial, not difficult also, but just let's put this as some information. Okay, so what we have done so far. Okay, now let's do some elimination of variable example for this application for this elimination variable. So this is problem number 9. So let me recall one thing from the lecture before doing the problem. So recall if phi from r x1 up to xn to r be defined by phi of xi equals to ai for some r, a ring homomorphism, is a ring map, then kernel of this ring map is basically the ideal generated by x1 minus a1, x2 minus a2, and xn minus an. Now let's use this to do the next problems. The proof is also easy. I think the same proof has been done in the case when R is a field, algebraically closed field, to give description of the maximal ideal of the polynomial rings over algebraically closed fields. So one can use the same proof here to prove the kernel of this homomorphism is the ideal generated by these polynomials. So the problem is what is the kernel of the ring map phi from q x y z to qx which is defined by uh, phi of x is equals to x, phi of y equals to x plus 1, phi of z is equals to x square plus 1. So now how to find some description of this kernel. Now one can use the other information. So let r equals to qx. Then this phi is actually a map from r y z to r, which is defined as phi of y equals to x plus 1 belongs to r, phi of z is equals to x square plus 1. This is also belongs to r. So kernel phi is basically y minus x plus 1 comma z minus x square plus 1. So generated by these two polynomials. So this is one description for the kernel. So this is by using just this fact which I have recalled. So I think we have done cover sufficient problems for this week. So it is better to stop now. So again, we will discuss some problems in the next week. Okay, so bye.